There are many different types of energy we can use in the future, renewable energy for making a sustainable society, to move away from fossil fuels. And we're looking at electrochemistry to create that sustainable energy. So we're looking at using electrochemistry to make hydrogen and organic fuels, and then we're also using electrochemistry to look at batteries. And we can use these two different systems in different environments where they might be necessary. So for the fuels, we can use that in transportation, and for the batteries, we can use that in transportation, but also in energy storage. When we're using electrocatalysis for generating fuels, this in itself is a sustainable technology, generating a sustainable fuel. So we're using solar energy or wind energy to split water, and water is an abundant resource. So we create hydrogen, which is then sustainable and CO2 neutral. In our group, we're also using electrocatalysis to generate ammonia. And currently, ammonia is generated in a really high energy intensive process. But if we use electrocatalysis, then we can do this at lower operating temperatures and pressures to make it less energy intensive. And we will use renewable energies, wind and solar, to put energy into the system and create ammonia. And ammonia can be used both as a fertilizer, but also as a fuel in the future. Another avenue of our research is to study the degradation in lithium-ion batteries, because in batteries, lots of gases are being generated, and this is bad for the performance and bad for the lifetime. And those reactions that are occurring that we want to inhibit are the reactions that we actually want to happen with electrocatalysis, so generating hydrogen. So we're using the techniques we have here to understand both these systems, so we can learn from each of them and optimize both of those systems. In the White City campus, we have some really highly specialized technology to study electrocatalytic reactions. And something we work a lot with is the electrochemistry mass spectrometry instrument. And this means that we can study electrocatalytic reactions as they are occurring. So we can monitor in real time if we're generating the products we want to generate, or if we're generating co-products. And that will help us really understand the reaction and how active our materials are. By using this equipment to study our different systems, then we can learn how to optimize these systems in a better way. And then this will lead to achieving our targets of net zero by 2050.
I'm Daisy Thornton. I'm a PhD researcher at Imperial, working in the Department of Materials, and I'm working in Evan Stevens's group. I'm working with Bethan to study the degradation in lithium-ion batteries so that we can try to optimize them. So as we use lithium-ion batteries, their performance begins to deteriorate. So in my project, I'm trying to understand the degradation mechanisms that contribute to this deterioration. Interestingly, a lot of these degradation mechanisms are accompanied by some form of gas evolution. So we're producing gases as a side product. And so we're using the techniques that we have at the White City campus to try to understand these mechanisms so that we can prevent them and ultimately have better batteries that last longer. Throughout my project, we've been working on adapting a novel technique that can probe this gas evolution as a function of electrochemical cycling of the battery. A lot of this work involved the development of a new cell so that we can actually build the battery and then study the gases that are coming off of it. And it was a really fun process to be able to file for a patent for this and to learn about the commercial aspect of our research as well. To complement the gas evolution measurements with the electrochemistry mass spectrometry, we're also carrying out a lot of surface characterization measurements and using the facilities in the materials department to really build a holistic understanding of these degradation mechanisms. With the insight and this increased understanding of these degradation mechanisms, we'll be able to build better batteries and implement mitigation strategies that prevent the degradation from happening in the first place. And this will hopefully be able to increase the uptake of electric vehicles and help us to be able to use batteries for more energy storage as well.